Hey, we are live now.
Okay, so let's wait 1 more minute.
Okay.
So that I'm sure not to lose the people really interested. Okay, so let me try to start. So as usual, so this is day 4, and today we will complete the study of equivalences. There are lots of things a lot more things to say about equivalences in homotopy type theory. And well, usually I start by reviewing what I did the day before. I will do it, but the organization of my slides make it such that I placed a few slides on an application of univalence right after the introduction of the notion of the axiom of univalence. So let me start from there. So this will be new material for like 10 minutes, and then I will review what I did the last time, and then we will go on. Okay, so my first reminder, because it's a reminder, is to recall the 2 axioms that we add to our basic type theory. The first one is function extensionality, which can be viewed as a characterization of the propositional equality for function types. So it asserts that this is exactly the notion of homotopy that we discussed. So for all x, fx is propositionally equal to gx. And then univalence asserts that the equality of types in the big type U, the universe of types, is characterized by A and by this type, which captures under the guise of this predicate by inv, okay, of this type by inv, which captures the equivalence of the types A and B, okay. And let me remind you now that by inv comes in 5 components: a function from A to B, that is f; a function from B to A, that is G; another function from B to A, that is H; and then eta, a proof that G is a left inverse of F; and epsilon, a proof that H is a right inverse of F. Okay. So as I also told, the axiom comes in the form of providing an explicit quasi-inverse in this direction to the map that we define in this direction by path induction. So I might review here shortly how we define this map. Okay, so this map, that is this canonical map that is defined by path induction and is called id to ECV here, is defined by, so id to ECV should turn an equality of A, a proof of equality of A equals B, so it should turn such a P into a quintuple like this one. And so we need a function from A to B. So P is a proof of A equals B. We need a function from A to B. We need a function from B to A, and then another one, and then an eta and epsilon. So for the moment, I just recall today. I just recall how I get the two functions, because of course, actually what I do is that I repeat. So the G and the H will be the same function. So I actually define only two functions, one from A to B and one from B to A. And they are defined using transport. So the definition of id to XZ, sorry, I was a little bit incorrect by telling you that it was defined by path induction. This one, this particular one, is not defined by path induction, it's defined by transport. Okay, transport is itself defined by path induction, but I mean, it's not directly defined by path induction. So how do we get from P easily a function from A to B? By using the identity family. Okay, so if you take the identity function from U to U, okay, it's a type it's a type family because it goes into U and it's indexed by U. Okay, and if I transport, if I look at what transport relative to this family means, well, it means that and along P, okay, it will, okay, so maybe I should write it. This is my base, this is U, okay, and above each type, I have one type, which is A itself, because id U of A is A, okay? And here I have my equality between A and B, that's P. So the transport here will transport relative to this id family along the path P, will take an element of A and transport it to an element of the fiber here over B, which is B. Hence, it's a function from A to B. And to define a function from B to E to A, I just first reverse the path P so that I get a function from B to A. So this is how E to XZ is defined. Good. And then this allows me to derive this property, which I shall be using later on. So let me first describe the property and then prove it. So the property that I want to use is the following. Okay, let me state the property. If I have a proof that two types are equivalent in the form of a bi-inv, okay, so it's F, G, H, eta, and yes, here's there's a small typo. There should be also an epsilon. Okay, but I don't care for eta and epsilon in what I'm telling here. So if I have yes, if I have a proof that A is equivalent to B, then what I can then I know that if I apply the univalence axiom to this E, then this is a proof that A is equal to B. And if I transport relative to the family edu, what I will get is the component f of E. And if I transport along the reverse of UA of E, I will get G and H. And the proof is just an immediate consequence of the definition of E to X V, which is here. So you see that the first component of E to XVP is transport EduP. The second component is transport EduP minus 1. Okay, so this is written here. By the very definition of transport, by the very definition of E to XV, these definitional equation holds. Okay, so now if I apply it to some UA of E, see, so far here there's no univalence involved, okay? But in this equation, there is univalence involved because if I instantiate in this equation here, if I instantiate P to be UA of E, okay? So UA of E is a proof that A is equal to B because let me remind you that UA goes the other way around. So it goes from A equivalent B to A equals B. So UA of E is a perfectly well type to be put in this position. So I can try to see what it means to transport along this path here, UA of E, and because of this, okay, because of this, transport UAE is the first projection of E to XV of UAE. Here I'm just instantiating this line with P being UAE, and then I use the fact that E to XV, the function computed, the function in E to XV UAE is just the first projection of E, which is S, okay, by definition. Okay, remember, E to XV gives me as first projection the transport. So this equation here is an immediate consequence of the definition of E to XV on one hand, and the univalence axiom because here, of course, I have used the fact that going from E to UAE and then to E to XV is the same thing as E. Okay. And projection, the first projection of E is just F. Okay, and the second projection of G is G. Okay, good. So my next slides, the next two slides is about trying to give you a motivation for univalence other than the Grothendieck equivalence, which I showed last week. And I'll come back to it a bit later because I realized that I should have given you a picture, and because this picture is helpful. So I'm apologize for not having given it yesterday, but I will give it today. So let's do this application. So the story starts like this. We want to endow some set with some structure. Here I'm speaking in ordinary mathematics. And okay, so for example, let's take the semigroup structure. Okay, so the semigroup structure can be captured in terms of type theory by saying that you have a type. So given a type A, you can define a new type, which is semigroup of A. And if you provide an inhabitant of this type, then you know that A is a semigroup. And Well, semigroup means just to have one binary operation, so an M of A times A to A. And then you just assume that this operation is associative. So you also provide a proof that at each X and Y, you have an equality if between, so this is X multiplied by Y multiplied by Z should be the same as X multiplied by Y multiplied by Z. So maybe it's easier to follow if I write it in this way. Everybody will recognize associativity. Okay, so this is a type describing the fact that I endowed A with the structure of the semigroup. Now, the question is, it's a general mathematical question. If I have, again, I speak set theoretically, if I have a set A, if I have been able to produce a semigroup structure on A, that's one thing. If on the other hand, I have a bijection from A to B, then I can sort of copycat or fax, or I don't know which image to use. I can transcribe these semigroup structures on B. Okay, and this is done usually. So if you look at mathematical textbooks, this is done usually in the following way. We want to define an operation on B, which will be associative. And the idea is that we start for defining this operation. So it should take two arguments, B1 and B2 in capital B. In order to define it, well, we use the bijections to the bijection from B to A to get the two elements in A. Then we multiply them in A, and we map them back to B. Okay. And then in mathematical textbooks, you would see an element. Well, this is quite elementary, but you would need a little proof to show that M prime is associative. Okay, so in univalent mathematics, things happen completely in the opposite order. So instead of having to define a semigroup structure on B explicitly, the univalence axiom will provide it to you as a gift, okay? And then proving that, but it will provide it to you as a gift, which is a little bit like a black box. So you will know by univalence that you have a semigroup structure on B, but nobody really tells you what it looks like. So if you want to uncover this formula, then you'll have some work to do. It's a no-win game. I mean, ordinary mathematics does the job at a certain point, and univalent mathematics does the job at another point in time. But in the end, they do the same kind of job. But what is interesting in univalent mathematics is that instead of having to guess this definition and check that it works, that is ordinary mathematics, homotopy type theory will synthesize this definition. So the idea is that univalent mathematics will tell you that there is a semigroup structure on B, and then you will be able to prove that this semi-structure is obtained in this way. So you can synthesize this definition. Of course, well, this is not a big deal because anybody would come up with this definition. But it's interesting conceptually to see that univalent mathematics provides you with something. And then if you want to see exactly what it is, you have to work. Okay, so let's see why this is the case. So I defined this type, semigroup of A. Actually, it's a family of type because for each A, I have a type like this. And Okay, and then if I have a proof that A is equivalent to B, okay, that's the type theoretic version of saying that there is a bijection between A and B. So if I have that E is a proof that A is equivalent to B, so essentially that I have inverse functions between A and B. And if I have a witness that A is a semigroup, then by applying transport to the type family semigroup, well, relative to the type family semigroup, along UA of E, so here I'm really using univalence. From this equivalence, I derive a path from A to B. Hence, I can use the technology of transport. So I can transport the couple MA, which is a witness of semigroup of A. I can transport it. So this expression here is of type semigroup B. Hence, okay, in one line, I'm able to show that B is a semigroup. Okay, but as I said, the work now starts, the real work starts to make sure that this semigroup structure is the one we expected. So is this one. And actually, it is not trivial. So it is, I have made the explicit proof here, and I will go through it slowly, just to show you that working with univalence and transport is a quite, if you want to do it very carefully, it takes a little bit of time and you use a lot of little facts. Okay, so let me do this slowly enough. So what we want to show is that the multiplication which I get on B from the general principles of univalence is defined as here. Okay, so what? So let me start from the beginning. This M prime, I define it explicitly as the first projection of this transport. Okay, because the transport yields a semigroup structure, so it's a sigma type consisting of the operation itself and the proof that it is associative. So for the moment, I'm only interested in synthesizing the operation proper. So I take the first projection. So I'm looking at this guy. Okay, and I want to start from this guy, to apply it to B1, B2, and to do a number of manipulations until I convince myself that it is equal to this thing here, which I was expecting. So you see, I have a sequence now, which I have to explain to you, that goes from here to here. Okay, so the first step is already a lemma. So let me tell you what this lemma is. Okay, so here we need to read this for the moment. So suppose I have a type family C, which is of this form. Cx is actually a sigma type, okay, whose first component is comes from some type family C1, depending on X, and whose second component comes from some type family C2, which depends on X and Y, because it's itself a dependent type. So suppose that my type family is of this shape. Okay. Suppose that I have, so this is a typo here, this should be an X1. Suppose that I have X1 and X2 of type A. Okay, so here it's the same A. This X varies over A. Okay, so it's here we have a type family that goes from A to U. This C. Okay, so suppose that P is a path in A, and suppose that A is an element in C1X1. and that B is an element in C2X1A. Okay, then, okay, in order to read these types, it's better to directly go to what I want to prove. What I want to prove is that if I transport relative to C along P a pair AB that belongs, because P is from X1 to X2, okay, this AB here belongs to, if I'm correct, it should belong to CX1, okay? Okay, so it's, let me write it explicitly because I want to be very slow in these slides. In this slide, I instantiate X with X1, so it's sigma Y dot C1 X1, C2 X1 Y. Okay, so so AB belongs to this type. So you see that A is an element of C1 X1. This is what I wrote here. And B, because I chose already and some A, okay, so this Y gets instantiated here to A. So B is really an element of C2 X1A. So I did not cheat on you by specifying these typings for A and B. They were the one expected by this formula. Okay, and what this lemma tells us is that if I transport, so here there's also a parenthesis missing, if I transport relative to C, this along P, this pair, and then take the first projection, then essentially B does not matter, and I could as well have transported just A relative to just the family C1 along the same path P. Okay, so this is again, as most of the time, this is proved by path induction. And the important thing here is to make sure that this is type checking. So let me type check it. So this A, as I said, is in C1 of X1, so it's written. So okay, so let's do it. So this A is in C1 of C1 X1. P is an equality from X1 equals X2. Hence, the whole transport here, maybe I use another color. The whole transport here will be in C1 X2, if I'm not mistaken. Okay, and here the transport here, well, we already checked that this whole thing is well typed. And so because AB is of type CX1, this guy is of type CX2. Okay, but CX2 is a sigma type. Hence, its first projection is of type C1X2. Okay, because it's I instantiate X with X2, so this X here becomes an X2, and the first projection is in C1X2, so I'm okay. This guy is also in C1X2. Good. So let's assume this property here, which I call double bar. Okay, so by the double bar property, because M prime is defined as the first projection of some transport, then I can remove the first projection and transport just along R, okay, which plays the same role as the C1 here. Okay, and if you remember what the definition of semigroup is, here, the first component is just A times A arrow A. Hence, my type family, the type family which plays the role of C1 here, is the type family that maps each X to X times X arrow X. Okay, it's a type family from U to U. Yes. So this guy is a type family from U to U. Okay. And while I'm here, I will also need this other type family Q, and I will also need the type family id. Okay. So at least we've got the first line clear here. By using this double bar property, I remove the PR1 and I change my type family from semigroup, which was here. Now I'm doing things relative to the family R. Okay, but here I can use an exercise that I think we even checked, or I think yes, I discussed it. So it was an exercise about explaining the transport relative. So maybe I repeat it somewhere here. If I have a bit of space, yes, I can do it here. So it was about if you have a family R, which is of the form. If you have a family R, which is of the form where you know that Rx. If you know that Rx is a Px arrow Qx, okay, so it's R is a pointwise arrow family of P and Q. Then I have a formula to define the transport relative to R in terms of the transport relative to P and the transport relative to Q. So here I'm applying this formula. With here, of course, one. So here I have to rename things. What plays the role of P is this family Q, and what plays the role of Q is this family id. Okay, because here it's really from the family Q to the family id. So if I apply this formula, then I get to this line. Okay, so transporting this B1, B2 consists in first transporting it along relative to Q, and then applying M, and then transporting according to relative to the family EDU. Okay, so now we have to remember from the previous slide, or 2 slides before, that transporting UA of something relative to edu is providing me with the function which is underlying the equivalence E. Okay, so that's good. So we can here. So remember that our E here we started from some E. Okay. Which was a proof of equivalence, so F, G, H, eta, epsilon. So transporting relative to edu, UAM, UAEM, all of this simplifies to F by what I just said. So this guy is just F, M, and the rest. The rest is not changed. Okay, so now what can we say more? Okay, so there is one more property which I did not write, but I cannot write everything. But you see that Q is pointwise the product of id and id. Okay, so of course, yeah, you have that because Q is just yes, X times X. So you see that we have formally. Let me write it just to be sure that everybody follows. Q, even if it's quite trivial, so Qx is it's a bit verbose, but let's be verbose. Okay, so we can write in a quite verbose way that Qx, which is x times x, is also like id_ux times id_ux, because id_u is the identity type family. So this is x. So there is another lemma which says that if you transport relative to a pointwise product family, the result will be a pair of the transports relative to the two component families. So we can decompose this Q here into id_u and give B1 to the left one and B2 to the right one. So this explains this line. And then I use again my magical property of univalence, which tells me that if I spot this expression, I immediately know that this is the function G, the inverse here. Okay, so here I can write G instead of this guy, and here I can write G instead of this guy here, and I obtain the formula which I wanted. So I hope this gives you a perspective. We spent a lot of work to justify this equation, but we spent no time in making sure that we had the semigroup structure on B. So that's I leave it to you as a philosophical comment. What is more important, to know that you have a semigroup structure, or to know actually how it looks like? And then if you want to know how it looks like, you have to work. Okay, so let me now go back to the review mode. So I want to review a little bit what we have done yesterday. And for this, well, I spent some time to explain you this theorem called the Grothendieck equivalence. And rather than recalling it formally, okay, I will do a picture, which I probably, I regret not having done it yesterday. So the Grothendieck equivalence is really about trying to match two different pictures. So there's this picture here of a type family, which I represent like with a horizontal arrow like this. Okay, so it's technically it's a function from Y to the universe. And this is one notion, and the other notion is a function from some x to y. So it's a pair of an x and a function from x to y. And the theorem, the Grothendieck equivalence theorem, says that this data is equivalent to this data. And one way to get easily convinced of this is to draw this picture. So when you see, so this was not by case that I gave a vertical version of this function, because, well, this gives rise to something that is called in category theory, it's called the fibration, but I don't want to enter in the categorical language, or just intuitively. Okay, so, but we already saw this picture when I discussed transport. So the idea in a fibration is that we consider that here this type Y is somehow a base of something. Okay, so you represent it on the bottom, and then over each element of capital Y, you draw a type above it. So you draw a space above it. Okay, you can call it a fiber. Why not? And as a matter of fact, what you take is, if you have this point of view that you started with an f from x to y, you just really take the fiber of f. And this is a type. So remember, it's defined by P. What was the type? It was sigma X of type X such that Fx is equal to Y. Okay, so that's one way. If you start from here, from this notion, you naturally have somebody to put in this position, namely the fiber. Now, if you have a type family, you also have a very, very easy way to put something in the same place, namely PY. Okay, and Grothendieck equivalence tells you that these 2 points of view that are written on the left and on the right are equivalent. Okay, great. So yes, if people want to raise their hand, I'm not necessarily going to see it because I'm too concentrated, but I think that one of the animators will see it and tell it to me. Okay. Okay, so let me.
Sorry. There's not a raised hand, but there is a question in the Discord chat.
Okay. Okay, so let me check if I can go.
I can read it for you, or I think Santiago is here in the room. He might be able to clarify his question.
Okay, so this way of defining similar as a product with a proof of association reminds of similar categorical constructions like monoidal and tensor category where the associated or not is part of the structure. In the categorical context, different associators would give in. Does the same happen, or if we change the proof of association, we will still have the same structure? The product is the same. Okay.
Oh, okay. I'm unmuted now, but you already read the question. So when you have this, so when you find monoids or the such categorically, you give a specific natural transformation, right? That functions as association. Changing this associator in general gives you a different monoidal structure or whatever. In this case, does changing the proof give a different structure, or do we have a propositional equality of this structures when changing the proof and keeping the product unchanged?
I don't have the answer. I should think a little bit. I think they will not be necessarily equivalent, just as if you have a category and a monoidal structure on it, you could have several ways of providing a monoidal structure with the same product. I'm not completely sure. I think it's not. Yes, it's really structure that you add, and hence you cannot expect that it is canonical. I would guess that the answer is just like in monoidal categories. So we should be careful. It's a structure of semigroup which comes with explicit proofs of associators and etc. And yes, but the question is interesting. I don't have a definite answer for it. Okay, so let's continue with the review. So the review was, what did we do else? Oh, okay, we spent a lot of time defining we started. So this I will not repeat. Well, I will not go into details again. I spent a lot of time to discuss the notion of proposition, the notion of contractible type, and then to show, and then also to discuss the notion of equivalence, the relation between being equivalent and being logically equivalent, and then I discussed the notion of set, And then I also discuss a whole hierarchy of types that have more and more structure, more and more higher structure. So this led me to this notion of H level or N type. And I gave a characterization of contractible types, okay, that are essentially propositions that are moreover inhabited. Okay, and I proved something that that I used over and over again, which is that every proposition is a set. And then I discussed the fact that being a proposition is a proposition, being a contractible is a proposition. And then, okay, then I discussed this, which I will, I'm revisiting now because I will use it later today. It's an interesting property of types, contractible types with respect to sigma types. So if you have a family of types, and if you consider the sigma types, then yeah, there are two interesting situations. Either you know that each of the px is contractible, in which case then the sigma type reduces to A. Okay, and I gave you an intuitive explanation, is that each p of x reduces to a point, so that above each point you have just one point. So you are somehow in this picture that I showed you just a minute ago. In this picture, every space that I'm putting on top is just a singleton. So what I'm sort of copying the space below into these fibers, and then this takes the total space. Okay, so I already gave you this name. This is called the total space for this family, and the total space gathers all these fibers all together, and you see that what we get here is a copy of what we had below. So that was one property, and the other property is that if A is contractible, then the sigma type is equivalent to any of the fibers. Okay, so I wrote it with center A0, but you know, as I explained to you, that you can take any element of a contractible type to be a center. Okay, and while I'm here, there is a nice consequence of 1 and 2, okay, which is namely, if I put together the two assumptions, so maybe I write it now because I will need it later. So if somehow it's a 1 plus 2, if I know that Px is contractible for all x, and if moreover I know that A is contractible, then I can put the two observations together, and I get that sigma x dot A Px is contractible. And the proof is actually, I don't even need, I don't even need the 2 in order to prove it. I just need the 1. So by the 1, using the fact that all the P of x are contractible, I know that my total space here is equivalent to A. Now, my second assumption tells me that A is contractible. And we have another theorem that I also mentioned yesterday, that equivalent types, if one is contractible, then the other is contractible. Hence, this is contractible. So we will use this a bit later. Okay, so yes, so I will not comment too much. Yes, so I explained you how we can start actually this hierarchy of types, not with is prop, but with is contre, because is prop is obtained from is contre in the same way as set is obtained from prop, etc. So that, and I also explained you why we start at -2, because this is -2 and this is -1, and set is 0, and set represents essentially a theory of zero-dimensional things, while 1 represents a theory of one-dimensional things like categories or groups, and etc. Okay, so then I showed also that there is a cumulativity property, and now this is written properly. There was a typo. That if some type is of some H level, then it is of any higher H level. And here there are two slides that I did not detail, and I will not detail them either because I need to move forward. But let me at least repeat or tell you the content. So just as we showed already that propositions are closed under the type constructions, and this is important to do logic, to do the Curry-Howard, because if we stay within the world of propositions, then everything is a proposition. If I form types out of propositions, but this applies to actually any n. So all n types are closed by the type constructions, and while the proof of these facts is not difficult, and somehow the story is you learn nothing new by reading. You will not learn anything new by me reading you these proofs in detail, but of course you will experiment with these techniques by reading them. Okay, another thing is I showed explicitly that being a proposition is a proposition, being contractible is a proposition, and more generally, being an n-type is a proposition. And again, this is quite easy, and I don't want to prove it. And now comes the point where we were more or less yesterday, trying to revisit or to visit more in depth the notion of equivalence. So I gave you two new ways of looking at equivalence. Okay, so the first one was having a quasi-inverse. The second one was being bi-invertible. In being bi-invertible, I do not insist that the left and right inverse coincide. In the half-adjoint equivalence, I insist not only, so it's stronger than Q-inv in the logical sense, in the sense that I insist on having one inverse, which is both left and right inverse. And moreover, I insist on having some coherence conditions. So here it's a proof of an equality that lives at the level of, so maybe we can specify this type to make this clear. So eta x is from, well, this lives, of course, because it's we apply f to it, so this lives in E. Okay, so here, this thing here tells me something in, yeah, okay, no. Because so you insist to have such conditions. That's this condition, okay. So that's the difference between is HAE and QInv. And the final one uses the notion of fiber that was essential in the Grothendieck correspondence. And I tried to give you an intuition. I say that F is an equivalence in case that I can show that each fiber is contractible. Okay, and I tried to convince you that it's intuitively saying to me that F is bijective. Okay, so now comes the actual work that I deferred to today, which is to prove carefully that these two other notions of equivalence are logically equivalent to the ones we already know to be logically equivalent. Okay, so that's one thing that I'm going to do. And then the other thing which I also announced yesterday is that among these four ways of defining being equivalent, three of them are propositions, and hence these logical equivalents turn into actual equivalences and can be used for univalence. So univalence, I formulated it with the by-inv because by-inv is by far the simplest. It's simpler to formulate than is half equivalence because you don't need any coherence, and it's simpler to formulate than contre map, which needs a notion of fiber, which is already a bit advanced. So it's pedagogically tempting to use be-ins, okay? And what I promise to you is to show that something is wrong with Q-inv, or to convince you that something is wrong with Q-inv, that we cannot add it here. It's here, clearly at the level of logical equivalence, it's here, but this guy is not a proposition, hence it cannot stand in a line with logical equivalence, because if I had another one here, this should be a proposition. Okay, so now we have to go and do the job. Okay, so technically what I will do is to prove yes, okay. I need, so how many implications do I need to show? I will have to show that being a Q-inv logically implies is half equivalence of F. So this direction. The other direction, I'm happy enough, it's complete, it comes for free. Because is half equivalence has one more piece of information. If I remove it, then logically I have the material of Q-inv. So my job for proving this equivalence will be finished as soon as I have proved this implication. And for the other one, I need the two implications. This implication and the converse. Okay, so before us, we have in front of us three logical implications to prove. And two of them, the first two of them, will allow us to have some fun, at least me to have fun explaining to you, because I will use some material which I really love to use, which are called string diagrams. So maybe it's the first time for you, for some of you, to see them, so I will try to go slowly. So what we want to prove is that if you have the data f, g, eta, epsilon, then you can synthesize also the additional data, which is called, we call it tau in general. This thing here, we call it tau. Okay, so we need to synthesize such a guy. So it happens that the argument that I'm about to show you is completely standard in category theory. It tells you, so I can tell you what it says in terms of category theory for those who know about it. It's that you have one very, yes, you have two ways to say that two categories are equivalent. One is to say that yes, one is to say that you have, so you have to, so let me use the language of category theory. And if you are lost, it's not a problem because I will not really need it. So you have two categories. You have two functors, F and G. Okay, so you have two ways to say that they are equivalent. One is to say that you have a natural equivalence from G composed with F to id, and another from F composed with G to id, and that's all. The second way is to say that you have two functors that together form something called adjunction. Okay, they are an adjunction in which okay, so sorry, I will not detail, but it's an adjunction in which in an adjunction you have two such maps. Actually, you have one. If I want to be precise, you have two maps exactly like this. Okay, so the other definition is that two categories are equivalent if I can produce two functors which are adjoint, and with an adjunction come two such natural transformations, and I require moreover that they are isos. Okay, so the important thing is adjunction here, but I didn't tell you exactly what an adjunction is, but believe me, being an adjunction involves exactly this notion of tau here, or a version of this notion of tau. Okay, so in other words, it's a standard categorical fact that you can derive something like tau from less information. And this is exactly what we are facing here. Here we are facing the existence of F, of G, of these two guys, but we don't know any good coherence between these two guys, but we are going to synthesize it. And how do you do it? It's actually not trivial to do it in category theory. Well, it doesn't take a lot of time, but I mean, not a lot of lines, but it needs a little bit of insight. And so what you do is you can't build the tau based on the original eta and epsilon. This you cannot do. What you have to do is you have to do some kind of massage to one of them. And well, typically, in general, you do it on epsilon, or actually you will do it on epsilon. So what we can show, and this is what I'm going to show now, is that if I have as a witness of being quasi-inverses, f, g, eta, epsilon, then I can keep f, g, eta. So far, I can keep this information. I have to modify epsilon to find a new clever epsilon prime, for which I'll be able to find a tau. Now, the proof of this is written here in classical terms. And I invite you to read it carefully when you will have the slides. Yeah, actually, I think that it's already there in the first version I sent the first day. But I will probably send an update tonight because there are many changes by now. Instead of doing that, which is, well, painful to check, I will introduce you to a way to do this purely in terms of nice geometric diagrams. Okay, so here starts the game. The game starts here. The definition, so here I have to explain a few things. Yes, I think I have enough time before the break to explain all this well. So I have a lot of things to explain. So maybe I use another color here. Remember, for example, that let's take epsilon. Let's take eta. Eta by definition is, if I'm correct, is a proof that G composed with F is homotopic to the identity. Okay, so the idea is that I will represent all this information in terms of diagrams, and the rule of the game is the following. In these diagrams, you will have strings. This is why it is called string diagrams. You will have strings like this one, like this one, like this one. And each of these strings will be a function or functor, but here it's a function. So it will be on arrow type. And the idea, okay, so this here stands for this string is colored with F, is colored with G. And one of the rules of the game is that if I have successive strings like this, one being F, the other being J, and the following being H, then it is also understood that F is from some type A to some type B, that G is from some type B to, G from the same type B to some type C, and H from the same type C to some type D. So you have to think that in these pictures, not only the lines or the strings are colored by something, in this case FGH, but also the portion of the space, delimited by strings. So, for example, in this picture, I have divided, because you also have to think of these strings as stretching completely up and down. So they are really separating the plane. So you see that here, that by these 3 strings, I'm separating the plane in 4 parts. And each of these parts will correspond to a type. Okay, just like here, A, B, C, D. Okay, so that's one thing also. And finally, I will have little operators like eta or like epsilon. Yes, or like the epsilon prime, which I'm seeking. Okay, I'm seeking here to define some epsilon prime. So I have operators, and these operators will appear in this form. So, for example, eta is going to be a proof that G composed with F is homotopic to the identity. Okay, or equal to the identity, because we have extensionality. So I will represent this by saying, okay, so there is a little operation that takes as argument F and G, because I'm reading what I have written so far, I'm reading this as G composed with S, okay? And this goes to the identity. So at the bottom, I have just, okay, so let me write names. It will be even more suggestive. So F, suppose that F is going from A to B, okay, and D from B to A. You see that in the end, this should go to the identity over A, okay? So here, we should end up in A. I mean, the space, if I remove this upper part of the picture, if I concentrate only on the lower parts, after I've done the operation, I do not divide the space anymore, because it is the identity on A. Also, the other idea is that if I have something called the identity of A, it goes from A to A, it is really not worthwhile to draw a string for that. Okay, it doesn't make any good geometric sense. This should be nothing. This should be the whole space. Okay, so with this intuition in mind, it is natural to draw something like this. So the eta will be a kind of an operator which absorbs F and G and do not have any exit. So maybe I should do this. Yes. So here, see, here I'm zooming it here as well. So this is my representation for eta. Okay, so this is a bit misleading that I have this eta that goes out of the circle. It should not. I mean, there is nothing, there's no string coming out. It's just the letter eta. So let me remove this little part here just to avoid any confusion. Okay, so I hope you get some idea of my representation of the data. So I know how to represent. So let me go back to my original problem. So I know how to represent the data of QInv, okay, which are F, G, eta, and epsilon in terms of little drawings. Okay, so I know how to represent F, G, they are strings. I know how to represent eta, it's an operation represented in this way. And similarly, I can represent epsilon, for example, that features here in the same way, except that I will represent, yeah, it's the same thing, except that eta has left y f and right y g, while epsilon has left y g and right y f. Because epsilon, of course, is from f composed with g to the identity. Okay, so with this preliminary, after these preliminaries, I can give you my encoding of epsilon prime. So remember what my goal is to devise an epsilon prime and to also devise a tau. Okay. So here is my definition of epsilon prime. So the idea then, of course, is to combine such little diagrams together. So I have at my disposal eta and epsilon, and I can combine them in this way. You can read, and there is a notion of type checking for these diagrams. So you need to check that locally everything is correctly typed. So this epsilon has to take a J and an F, etc. You have to check all the to make type checking everywhere. So you can assemble epsilon eta and epsilon -1 in this way, and it works. Okay, so let's do it. If I first put this epsilon -1 here, then it out of it goes some G and some F. Okay, but this G could be the right wire for an eta. Okay, so I can put an eta here, and finally I can join also this F. I can put an epsilon here, and for this I need to add a string here. Okay, so this diagram is well formed. Okay, I don't give you all the rules for forming diagrams. I hope to rely on some intuition here. But what is important here is to look at the whole picture, and the whole picture, what does it tell me? Is that if I look from outside, if I don't want to enter into what is inside, I see that I have something which have two entries, this one and this one, and this is G and F, and has no exit because epsilon is closing everything. So eta was already closing a little bit of things, and epsilon is closing the rest. So there is nothing out. So this is correctly typed to represent to be a correct definition for epsilon prime, which expects to have this shape. Okay, so now next step is that we need to provide a proof that we need to provide tau. So in which form shall I provide tau? I will provide a proof that, so I have now to remember what tau is. Tau, okay, tau should be a proof that f of eta x is equal to epsilon fx of fx. So here I shall take profit of my tablet, and I will copy this information so that you don't need to memorize it. Yes, so here, let me put this information here. No, he didn't want to copy. Why? I don't know. Sorry, I have to do it again. I tried to be very technological, but sometimes it doesn't work. Probably I missed some steps, but this time it should work. Okay, so this is our goal now. Our goal is that, and of course this should be for the new epsilon prime now, because we changed epsilon in order to check this. Okay, so I want to prove this equality. And for this, I will do a number of transformations on that go from the left to the right. So first of all, let me try to convince you that this guy here corresponds to this picture. Well, first of all, one nice thing about string diagrams is that if you are not required to, you not necessarily need to do things point by point. Well, in the next slide we will need to do it, but in this slide not, in this implication not. So we can ignore the x, okay, and just try to see what it means to do first f and then epsilon prime. Okay, but this is easy. You just do f first and then epsilon prime. Okay, so this picture here represents this right-hand side. On the other hand, this one says do eta first and then f. So you put eta and you put f after it. Okay, so maybe I add the missing information. This is an f and this is a g and this is an f. Okay. So my goal is to convince you that I have a way to transform this diagram into this other diagram. And for this, I will need an auxiliary property, which is written here. It's written here. So I need to be able to prove, yeah, probably it's better to put an equal, because these are not definitionally, it doesn't correspond to definitional proofs of definitional equality. It really corresponds to proofs of propositional equalities. Okay, so I need a lemma, and this lemma is saying that doing eta first and then f and then g is the same thing as doing f first, then g, and then eta. Okay, so the first thing to notice is that these two diagrams have the same shape, the same external shape. So they both take 4 wires in input and 2 wires in output. 4 wires and 2 wires. And moreover, they have the same type. FG, 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 FG. Okay, so how do we prove this? So this is a bit magical. First, we know that eta is an iso, okay, because that's part of our axiomatics. So we can write that, we can write the eta, and we also can write its inverse, okay, and put the inverse of eta just below eta, like here. And because they are inverse, they are composition, okay, so the fact that writing it below means that I want to compose them. So composing them, because they are inverses, yield me the identity. Hence, this is the identity. Okay, when I have a natural transformation that is the identity, I do nothing. So these two guys combined together reduce to these two strings. And now comes an enormous magic of string diagrams, is that when you have a string diagram, you are allowed, it's why it is called strings, you know, it's like, you know, puppets. So if you play with Puppet, if you are really a professional Puppet player, you can do everything with your strings, except that you cannot pass a string. So you cannot, for example, here, from in this picture, unless I use some extra property, I have no way to push this across this line here. This line is a severe boundary. It's a really severe boundary. So in a string diagram, you are not allowed to pass a string if you have a string in front of you. But here you see that. Sorry. So it means that this guy here, you can move it quite freely. The only thing that you cannot do is, well, you can also move it here. Okay, I don't have enough space, so let me give a bit more space just to try to convey the idea. You can even move it a little bit here, okay? But if you do it, then you will never be able, for example, to cross this F. Okay, that is impossible because there is a string. But as if I don't go in this direction, but just go in this direction, then it's okay. So this is what I'm doing here. I'm moving this guy just here. And then I'm exploiting the fact that eta and eta minus 1 are again inverses. So I can cancel them out and I get this picture. Okay, so we have proved this lemma, if you accept this kind of graphical proofs. Good. Now let me finish and then we make the break. I want to remember that my goal is to go from here to here. Okay, so the first thing is to expand the definition of epsilon prime. So here I just insert this diagram and put an F in front because it was F in front of epsilon prime. So I have this diagram here. And in this diagram, I recognize this box here, which is a subpart of the diagram, which is exactly the right-hand side here. Okay, eta with in front of it a G and an F. Hence, I can apply this rule, which I just proved. And after application of this rule, the eta goes to the left. And then what is left is two wires, these two wires. And I have to attach what remained of the diagram. So I just did the change in this box here. But I have to attach what was outside, namely this epsilon and this epsilon minus 1. And I have to attach them to the wires that have been unchanged because the change is local to here. So I knew that this epsilon was attached to the second wire coming out of the box. Okay, so the new box is this one. This is the new box. Maybe I should draw the box in order to make things even clearer. Okay, so this epsilon, the left part of epsilon, should be attached to the second wire coming out of it. So I put it exactly as specified at the second one. This epsilon minus 1 should be wired to the 1, 2, 3, 4th wire coming into the box. 1, 2, 3, 4, this one. Okay. And what I recognize now is that epsilon and epsilon minus 1 are just in contact with one with the other, which was not the case here. There was an eta in the way between them. Okay, this eta didn't allow to epsilon and epsilon minus 1 to communicate. But after this transformation, now epsilon and epsilon minus 1 happen to. Maybe I can remove the box now to make even, the box was useful to, but I don't know how to remove the box. Okay. So anyway, now epsilon and epsilon minus 1 can cancel just in the same way because they are inverses. Okay, just as I used here. So I can cancel them out. And what I get instead is the identity, okay? But this identity is not witnessed by any string because there is no incoming string here and no outgoing string here. So this cancellation is just nothing. And hence, what remains is just this part of the diagram, which is what I wanted. And hence, you see that I have justified this equality, which means that I have synthesized tau. Okay, and this is the way to do it without string diagrams. And here we can make a break and start again in 10 minutes sharp from now.